You know, when you think about spaceflight, you're probably picturing massive rocket engines, mind-bending orbital mechanics, maybe some zero-G acrobatics. But there's this hidden battle that every single spacecraft has to win, and that's the fight against its own electricity. Today, we're going to dig into a really foundational 1975 NASA report that basically wrote the rulebook for taming high voltage in, well, the toughest environment you can imagine.
All right, let's just jump right in with a number that honestly stopped me in my tracks. Back in the early days of space exploration, what percentage of high voltage system failures do you think were because of design flaws that were totally preventable? Well, according to NASA's own studies, it was a staggering 75%. And hey, don't just take my word for it. Here it is, a direct quote from the preface of the report itself. This wasn't just random bad luck, or some stray cosmic ray causing problems. No, this was a consistent, recurring engineering challenge, a puzzle that absolutely had to be solved if we were ever going to reliably explore the solar system. So that brings us right to the heart of the problem. What exactly were these engineers fighting against? Let's define the threat. So this enemy, it has a name: voltage breakdown. The easiest way to think about it is like a miniature lightning strike. It's this unwanted, really destructive spark that jumps between 2 points that it should never touch. And in the super tight confines of a satellite's electronics, a single one of those little arcs, yeah, that can mean mission over. But to defeat an enemy, you gotta understand it first. Why do these sparks happen in space, of all places? Well, the answer is hiding in some pretty fascinating physics about gas and pressure. Okay, now this U-shaped curve you're looking at, this is Paschen's law, and it is the key to this whole thing. It shows you how much voltage it takes to make a spark at different pressures. And here's the part that's going to bend your brain a little. It's actually easiest to create a spark not down here at sea level, and not in a perfect vacuum, but in that weird partial vacuum right in between. So the crazy thing is that both ends of that curve are pretty safe. Down here on Earth, the air is so dense that the molecules are all packed together, kind of like a traffic jam, and they get in the way of a spark forming. Then, way out in the near-perfect vacuum of deep space, there are so few molecules that there's just nothing there to carry a spark across a gap. So both are actually great insulators. And this is where it all comes together in the real world. As a rocket blasts off, it has to fly right through the bottom of that U-shaped curve, in altitude somewhere between 30 and 65 kilometers up. They call this the corona region, and it's where the air pressure is at that perfect terrible level that lets sparks form at much, much lower voltages. It's a gauntlet that every single spacecraft has to run. Okay, but here's the real kicker. The danger isn't just outside the spacecraft during launch. The very same physics can create a tiny, localized danger zone inside the hardware itself, and it's all thanks to a microscopic villain: bubbles. See, to protect electronics, engineers will often embed them in this solid, insulating material. It's a process called potting or encapsulation. But if you're not incredibly careful, you can trap tiny bubbles of gas inside. And as this model from the report shows, you can wind up with one of these voids, these little bubbles, right next to a supercritical conductor. And inside that tiny microscopic bubble, well, it's a little pocket of low-pressure gas. It's a miniature version of that dangerous corona region we just saw up in the atmosphere. You've essentially created a tiny lightning storm just waiting to happen, buried deep inside your mission-critical electronics. It's kind of terrifying, right? So how does this tiny little bubble become a mission killer? These diagrams show its deadly journey. As a bubble rises through the potting gunk before it hardens, it expands. That expansion makes the pressure inside it drop, tracing a path right down into the danger zone of that Paschen curve. And when it hits that line, zap, voltage breakdown, failure. So how in the world do you fight an enemy that's literally invisible? Well, you fight it with an incredible amount of precision and care. This is where the engineers came up with a whole toolkit of techniques to build systems that were totally space-proof. The solutions are all about paying fanatical attention to detail. You use potting materials that are really runny, almost like honey, so bubbles can escape. You mix and pour them in a vacuum chamber to literally suck all the gas out. You get rid of any sharp points on metal parts because sharp points act just like tiny lightning rods. You even cut slots into circuit boards just to make any potential spark have to travel a longer, harder path. And speaking of lightning rods, get this.
even a microscopic bump on what looks like a perfectly flat metal surface can concentrate the electric field by a factor of 1,000. It's just a powerful reminder that at these voltages, you need a level of perfection that's totally invisible to the naked eye. It's absolutely required. All right, so after all that theory and all this meticulous work, does it actually pay off? Let's wrap this up by looking at some real-world hardware that actually flew, proving these principles really work. Check this out. This is a 1,500-volt power supply. Now, its designers had a problem. As the unit heats and cools in space, the potting gunk and the aluminum case expand at different rates, and that can cause cracks. So what was the solution? They filled the potting compound with these tiny glass microballoons to make its thermal expansion match the aluminum perfectly. Just brilliant. And here are two totally different ways to solve an even higher voltage problem. On the left, you've got a unit where the components are held up by these special corrugated standoffs. Those ridges just increase the surface path a spark would have to travel. And then on the right, a completely different idea. They just got rid of the potting altogether and machined the parts themselves out of a special spark-resistant plastic. So cool. So, the big takeaway here is this. Building electronics that could survive in space wasn't just about making them small or tough. It was about deeply understanding the fundamental physics of electricity and pressure, and then applying that knowledge with this meticulous, almost fanatical engineering discipline. It's really an incredible story, right? This hidden battle fought on a microscopic scale. So maybe the next time you see that beautiful footage of a rocket climbing through the sky, you'll think about that dangerous corona region it has to push through and all the invisible sparks its designers worked so hard to tame.